Okay, hello. So this video is meant to just explain all of the written solutions to the practice final exam. So you should be able to find this sheet of written solutions on Canvas, and I'm just going to sort of talk through it. So the first question says, suppose we have used sample data to create this 95% confidence interval for mean height of adult females. And there's the interval 62.5 to 66.7, and the question says, identify which null hypothesis would result in which p-value from this list on the right. And so the first thing I've done on these solutions is eliminate the ones that can't possibly be right because they can't be p-values. So this first one is negative, can't have a negative p-value. These two are bigger than 1, can't have that either. P-value is a probability, so it's between 0 and 1. Now as far as deciding between these remaining three, well, one of them is less than 0.05. So one of them is going to be correspond to a hypothesized value that is outside of the corresponding 95% confidence interval, and this value here, mu equals 67, that is outside of this confidence interval. It's just to the right of 66.7. So that's got to be the smallest p-value, and then you've got to decide between these two. You've got a bigger one, 0.7 something, and a smaller one, 0.13-ish. So think about how far away the sample mean is from the hypothesized mean. If the sample mean is really close to the hypothesized mean, the p-value will be bigger. The p-value gets smaller the further away the sample mean is from the hypothesized mean. The p-value is the probability of getting results at least as extreme as the ones you got if the null were true, and by extreme we mean at least in this much disagreement with the null. So the farther the sample mean is from the hypothesized mean, the smaller the p-value is going to be. The sample mean is the center of this confidence interval, and between these two possible hypothesized values, 65 is closer to the center. 63 is almost outside of it. 63, this left endpoint is 62.5. 63 is almost outside this confidence interval. So it's inside the interval, but it's just at the edge, whereas 65 is closer to the center, and so it's going to have the larger p-value. Okay. Next question says, why do we say that a small p-value provides evidence, or stronger evidence, for a scientific hypothesis than a large p-value provides for full credit? Your answer should refer to the logic behind how a p-value is used to provide evidence. So what it says here is that p-values give the probability of obtaining a test statistic at least as extreme as that which you got, or at least as large as the one you got. It means the same thing. Assuming that the null hypothesis is true. So if you get a small p-value, it means you obtained results that would be unlikely to occur by chance if the null hypothesis were true. You can go back to that lady tasting tea example from the very, very, very beginning of the hypothesis testing notes. The story of the lady tasting tea, this woman said that she could, by tasting a cup of tea, tell whether the milk had gone in first or the tea had gone in first, and they did a blind taste test, and she drank, she sipped from 8 cups of tea, 4 of which had the milk in first, 4 of which had the tea in first, and she got them all right. And so the logic is, well, if she was just guessing, then she shouldn't have gotten all these right. Or the probability of her getting all of these right if she was just guessing is small, and so we don't think she was just guessing, we think she actually could tell the difference. This is the logic here. If you get a small p-value, then the thing that happened is something that would be unlikely to happen if the null were true, and so that's evidence against the null. Whereas if you get a large p-value, you're saying the results we got are the sorts of results that we would expect to see if the null were true. Doesn't mean that you necessarily believe the null is true, or that a small p-value is evidence that the null is true. It's just, a large p-value is evidence that the null is true. It's just not evidence against the null. And so that's the logic behind how we use p-values to provide evidence. Okay, number 3, we've looked at a lot of hypothesis tests over the semester. The box on the right here contains brief descriptions of how test statistics are calculated for various tests. and then for parts A, B, and C, match the given null hypothesis to the appropriate description of how to calculate its test statistic. And so this, when I first printed this out, I had bad wording, and I went ahead and changed it. So the blank version that you should see that's on Canvas doesn't have this scribble here. But the first one, let's go through these instead. Let's go A, B, C. So A, beta 1 equals 0. So beta 1, that's a regression coefficient. It's a slope coefficient in a linear regression model. Population slope, and when we test to see if a predictor variable is significant, what we're really doing is testing to see if the slope for that predictor variable is significantly different from 0. And we do this with a t-test. All t-tests that we've seen, all t-test statistics are constructed by making the numerator be the estimate, the actual effect you measured in your data, and make the denominator the standard error of the estimate. And so this is the test statistic that tests against this null. It's B1 divided by the standard error of B1. Well, there it is. The estimated value of the slope divided by its standard error. B1 is the estimate for beta 1. And then for B and C, we have to choose between mu sub d equals 0 and mu1 minus mu2 equals 0. So mu sub d is for a paired test. The d means difference. This is the mean of the differences in a paired design where each subject is measured twice. Whereas mu1 minus mu2 refers to means of two entirely different populations. This is when we drew a sample from one population and drew a sample from another population. Or, more practically, when we take a sample and we randomly assign individuals to two different conditions and then do something different in the two different conditions, like control versus treatment. We then say the control group is like a random draw from the population of all people who would be subjected to control. The treatment is like a random draw from the population of all who would be subjected to treatment, but the key here is we have two populations. So 1, the sample means and standard deviations for both groups are calculated individually, and then the difference in sample means is divided by the standard error of the difference in means. This is this. The key here is that we have these means being calculated individually. So there you go, the numerator here, x bar 1 minus x bar 2, the means of two separate groups calculated individually, as opposed to Roman numeral 2, the sample mean and standard deviation of the differences between the paired observations is calculated. There's that word paired right there. That's sort of the dead giveaway. And so this mean here is the mean of the paired differences. This SD is the standard deviation of the paired differences. Okay, 4. This is a long one. This is a pretty long regression one. So the SAT is a standardized test taken by high school students before applying to college. There has been a lot of research and controversy regarding what kinds of factors might influence SAT scores. This page and the next refer to data on SAT results from every state in the country, and the following variables are used. So total SAT is average combined SAT score. By combined, we mean the math and verbal sections for that state. Expenditure, average expenditure per student in thousands of dollars for that state. Student to faculty ratio, the average number of students per faculty member in that state. And percent taking, the percentage of students who take the SAT in that state. Okay, and then we have 4 regression models. The response variables in 3 of them are this total SAT value for A, B, and D, and then for C, the response is this percent taking variable. Okay, A says below are 5 scatter plots with labels and axes missing. 4 of these scatter plots correspond to one of the 4 models above, with the predictor variable on the horizontal axis and the response variable on the vertical axis. One scatter plot does not refer to any of the 4 models, and then label each of them A, B, C, D, or none on the lines provided. So the way to go about this, the first thing I would do is look and see which of these slopes are positive and which are negative. So over here, the predictor variable is right below intercept, and we've got a negative in model A, we've got a negative in model B, we've got a positive in model C, we've got a positive in model D. So models A and B have to be graphs with negative slopes. Well, let's see, this one's negative. This one's negative. There's only two negative ones. Okay, so B, we got to decide between B and A, between these two. And the way you figure it out is, in this one for B, the data are a lot closer to the line. In this one in A, the data are a lot more spread out around the line. And the statistic that visually quantifies how spread out the data are around the line is R squared. SSE will do it as well. If I'd given you sum of squared errors or mean squared error, you could have used that, but I didn't give you that. I just gave you R squared. The interpretation of R squared we've been discussing in class is it's the proportion of variability in the response that's explained by the predictor variable, but visually that's just the data being closer to the line. So this value of R squared is 0.14. This one is 0.78. So the R squared is a lot bigger in Model B than it is in Model A. Don't be fooled by the fact that the slope is larger for Model A than it is for Model B. That doesn't mean anything. These are different variables in different units, expenditure versus percent taking. The key is the R squared. So this has to be the large R squared. This has to be the small R squared. Now, as far as the positive ones, I've got 3 plots with positive slopes, but I've only got 2 models to choose between. And again, I can't go taking the raw value of the slope too seriously. You know, this one is 11, and this one is about 4. Sounds like this one should be steeper, quote unquote, but remember, we're dealing with different variables, so the scales of these axes might be completely different. Student to faculty ratio versus expenditure in thousands of dollars. These are completely different variables. This has a response variable of percentage of students taking the exam. This has a response of total SAT score. Again, these are totally different variables and totally different units on totally different scales. So I can't just visually look at these lines and decide which is which, particularly because the axis labels are not even on these plots. So let's look at the R squareds again. I've got a 0.345. I've got a 0.013. So I've got a very, very small R squared here for Model D. And I've got kind of a moderate R squared for Model C. I certainly don't have any R squareds anywhere near as big as the one for Model B. So if we look at the 3 remaining positive sloping plots, this one, this one, this one, this one here, the data is just way too close to the line. This looks like a very large R squared. This looks like it might even be larger than this R squared, and we saw that this R squared was like 0.78. So this has to be the one that's not being represented. Neither of these R squared values are big enough to look like this data. So the 2 remaining are this one and this one, and you can probably see pretty easily that while the data aren't really close to either of these lines, in this case, the data are so spread out, it almost looks like there's no correlation at all. Whereas this one, the data are still pretty spread out, but there's also a clear positive correlation. So this one looks like no correlation, this one looks like some correlation, so this one has the teeny tiny R squared, this one has the moderate R squared. Okay, A and B say on the top left plot above, draw a set of bands that could realistically be 95% confidence bands for a mean, and then C says on top of the middle plot, draw a set of bands that could realistically be 95% prediction bands for an individual observation. So you gotta know how to distinguish between these two things. Confidence bands for a mean, they're meant to capture the population line of best fit. We did a segment towards the beginning of the notes on inference and regression that discussed the sampling distribution of a line of best fit. When we take data to estimate a regression model, we're supposing that there exists such a thing as a population line of best fit. We have a population intercept, a population slope, we got an x and a y variable, that defines a line. Whether you really believe in such a thing as a population line of best fit is another story, but it's analogous to assuming that there's such a thing as a population mean mu, and then taking the sample mean x bar and treating it as an estimate. So, if we want to make an interval that's going to capture, we want to distinguish between 2 kinds of intervals. One is supposed to capture the population line, and then the other one is supposed to capture, this 95% prediction band is supposed to capture 95% of the raw data itself. So if you're making an interval that's supposed to capture most of the raw data, it's going to have to be a lot wider than an interval that's just supposed to capture the population value. And so visually, the 95% confidence band those are gonna be closer to the line than the 95% prediction bands. In particular, the 95% prediction bands ought to be capturing about 95% of the data, whereas the 95% confidence bands, as opposed to the prediction bands, the confidence bands don't care at all about capturing the data. The point is not to capture data with the confidence bands. The point is to make an interval that is made using a method that 95% of the time would capture the population line. So when I draw these on here, this first one is supposed to be bands that capture the population line of best fit, and then this one's supposed to be bands that capture 95% of observations. Not necessarily these observations, any observations we could draw, but they're always going to end up looking like they capture about 95% of the data you're looking at. So I drew this so that it looks like it's excluding only one data point and capturing all the rest. I drew this so that it's capturing lots and lots of data, because it's not supposed to capture data. It's just supposed to capture, it's just supposed to go around the sample line in such a way that we think it's going to capture the population line. Not that we know where the population line is. Okay, D, write out the formula for the estimated line of best fit for predicting total SAT using expenditure. So I just got to go up here and see which one of these predicts total SAT using expenditure. Well, I see expenditure here and expenditure here, and then, response variable total SAT as opposed to percent taking. So model A is using expenditure to predict total SAT. And it's just, there's the intercept, 108.12 roughly. There's the slope, negative 19.94. And so it looks like that. Intercept minus slope times expenditure. Create an approximate 95% confidence interval for the slope in Model D. Using this confidence interval, state whether the null that beta 1 equals 0 can be rejected, and briefly justify your answer. So the way we make a confidence interval is point estimate plus or minus margin of error. The way we make an approximate 95% confidence interval is to get the margin of error, you take the standard error and you double it. So 2 times the standard error is roughly the margin of error for a 95% confidence interval. It's not exact. If the sample size is bigger, the critical value will be less than 2. If the sample size is smaller, it'll be greater than 2, but it's almost always pretty dang close to 2. So when we do these by hand in this class, we're just doubling the standard error to get the margin of error, and then you add and subtract that to and from the point estimate. Well, it's a 95% interval for the slope, so I'm going to take the sample slope, add and subtract this margin of error. So for Model D, let's see, there's the slope right there, 3.71. There's its standard error, 4.82. So I double the standard error, I add and subtract it to and from 3.71. And if you do that, you should get this, negative 5.93 to 13.35. If we're going to use a confidence interval to decide whether to reject or fail to reject a hypothesis test, we check to see if the hypothesized value is inside or outside the confidence interval. If the hypothesized value is inside the confidence interval, you fail to reject it. If the hypothesized value is outside the confidence interval, you reject it. In this case, the hypothesized value is 0. 0 is inside the interval, and so we fail to reject the null. Next one says, calculate the test statistic testing this null that the population slope is equal to 0 in Model B. Using the p-value, decide whether we should reject or fail to reject this null hypothesis. So for Model B, here it is. As far as the test statistic goes, well, you can see I blocked it out. The test statistic is called t-ratio in JUMP. Where this t-ratio comes from, what's it a ratio of? It's a ratio of the estimate over its standard error. Actually, just talked about that in a previous question. So negative 2.44 divided by 0.19 is going to give you the t-test statistic. The p-value is really, really small, less than 0.0001. It's actually, in this case, a lot less than that. Because the t-test statistic is so huge, we get negative 2.44 over 0.19 gives you negative 12.84. That's enormous. We talk about size of a test statistic in terms of how far away it is from 0. So I'm calling this big. It's a big negative number. And so the p-value is very, very small, and if the p-value is small, you reject the null. Okay, G, how much does the predicted percentage of students taking the SAT change when per student expenditure increases by $1,000? This language of how much does this thing change when this other thing increases by a certain amount, that's the language of the slope. Now, in general, the slope is the predicted change in the response variable for a 1 unit increase in the predictor variable, and this doesn't say $1, it says $1,000. Oh my God, what's going on? Well, let's go up and take a look at how the variable is defined in the first place. Expenditure. Average expenditure per student in thousands of dollars. So an increase in this variable called expenditure, an increase of 1 in this variable is actually an increase in $1,000 average expenditure per student. It's just the way the variable is set up. So we're talking about a slope. And we want to relate SAT to per student expenditure. So we got to find the model that has that in it. Let's see. Oh, and I'm sorry, I shouldn't have said SAT. I was being a little bit too vague there. It says predicted percentage of students taking the SAT. So not SAT score in this case. This language is telling us that the response variable is percentage of students taking the SAT, so that is model C. There's my response variable, percent taking, and there we go, there's expenditure, the predictor variable, and there's the slope, 11.38 roughly. So that is a predicted change. It's not a predicted change in expenditure, it's a predicted change in the response variable, percent taking. So we're saying as expenditure increases by $1,000 per student on average, we see an associated increase in the percentage of students in that state taking the SAT of about 11.38%. Okay, and there's the 11.38. Okay, H. All of the plots on the previous page have lines of best fit superimposed on them. Suppose that on one of these plots we were to draw some line other than the best fitting line. What mathematical property would this line have that would distinguish it from the quote-unquote best line? This goes back to what do we mean by best? And this actually goes back to how we find the values of the intercept and slope in the first place that give us the line that goes through the data. We didn't get into any sort of mathematical detail on this. In this class, the extent of what is in the notes is that the best fitting line is the line that makes SSE, the sum of the squared errors, be as small as it can possibly be. It minimizes the sum of the squared errors. When we say the line of best fit minimizes the sum of squared errors, what we're saying is that, or what we're implying, is that if you were to draw any other line through the data other than the best fitting line, that other line is going to have a larger sum of squared errors associated with it than the best fitting line. As a reminder of what sum of squared errors is, visually, here I'll just draw this and then erase it. So visually on one of these plots, maybe I'll go down here, all of these vertical distances between every single data point and the line, that's an error, or actually we call it a residual as well. And there are questions where you calculate residuals. So the residual is the difference between the observed value of the response and the predicted value. The predicted value is always on the line. And so we take all of these residuals or errors, we square them, we add them all up. And the idea is this line right here is making this sum of squared errors be as small as it possibly could be for this data set with a straight line drawn through it. If I drew a different line somewhere else, if I drew it right here, then my sum of squared errors would be bigger, is the idea. Okay, I. Suppose we want to modify Model A. Let's go look at Model A. Model A has total SAT, so the average total combined SAT score in that state as the response variable, and expenditure, so this is per student average per student expenditure in thousands of dollars as the predictor variable. Okay, so we want to modify model A so that it could estimate the relationship between expenditure and total SAT in states for which more students take the ACT than the SAT, and in states for which more students take the SAT than the ACT. So we want to compare two different kinds of states here. Typically, states in toward the eastern side of the country, students take the SAT more often, and out west, students take the ACT more often. It says we could do this with an indicator variable. We can call this indicator variable just ACT, and we'll make ACT be equal to 1 if more students take the ACT than the SAT, and we'll make it be equal to 0 if more students take the SAT than the ACT. So this question is relating to that last set of notes on using categorical predictors in regression. We have an indicator variable. An indicator variable takes in the value of 0 or 1, and it indicates which one of two categories each observation falls into. So the first part says, write out what this model would look like generically if we wanted to allow for both the intercept and the slope for expenditure to be different for ACT equals 1 versus ACT equals 0. So if you think back to those notes on regression using categorical predictors, the first example we saw, was predicting resting heart rate using age, but then separating by 3 different sports. And the first example we saw was the one with the 3 parallel lines, and that was one where we estimated a single slope for age, and then we had these indicator variables for the sports that would allow the line to like shift up or down. But if we want to be able to have both the intercept and the slope for expenditure being different for the 2 different groups, then we have to put this thing called an interaction term in the model. We have to take the variable expenditure and the indicator variable ACT and multiply them by each other. And what this is going to do is it's going to create a term that will allow the slope to be modified when ACT equals 1 relative to when ACT equals 0. And so this is what it looks like in general. This top line is writing it out as though it's the estimated model with the B's. The bottom line is writing out as though it's the population or theoretical model with the betas. It doesn't really matter which one you use, although if you're going to be writing betas in here, you're going to have to tack on that plus epsilon as well. That stands for normally distributed random variation around the population line. That's only in the theoretical model. In the estimated model, our equation is just the line itself, no term for random variation around it, and so we just have the B's and the predictor variables. So I've got intercept B0 plus B1 times expenditure, B1 being the slope for expenditure, plus B2 times ACT. So ACT, it's an indicator variable. It basically turns on or turns off. If ACT equals 0, this whole thing goes away. If ACT equals 1, then I have B2 times 1, and B2 ends up getting added to B0. And then finally, B3 times expenditure times SACT. So again, if ACT equals 0, this whole thing just goes away. If ACT equals 1, I've got B3 times expenditure times 1. So B3 times expenditure. And so now we'll have expenditure being multiplied by both B3 and B1. And so B3 will be the amount by which the slope for expenditure changes when we're looking at a state for which ACT equals 1 compared to a state for which ACT equals 0. Okay, and then the second part says make up values for the relevant slopes such that the slope of expenditure is negative 20 in states where more students take the ACT than the SAT, in other words, states where ACT equals 1, and negative 18 in states where more students take the SAT than the ACT, in other words, states where ACT equals 0. That's how we coded up this variable. ACT equals 1 if more students are taking the ACT. ACT equals 0 if more students are taking the SAT. So if I want it to be negative 20 when more students are taking the ACT than the SAT, okay, what I'm saying is I want it to be negative 20 when ACT equals 1. When ACT equals 1, I've got the B1 times expenditure in the model and the B3 times expenditure, so negative 20 needs to be the sum of B1 and B3. Now we want it to be negative 18 in states where more students take the SAT than the ACT. So this is when ACT equals 0. So when ACT equals 0, this whole term here disappears, goes away, and the slope for expenditure is just B1. So basically, I want B1 to be negative 18, and I want B3 to be whatever I have to add to negative 18 to turn it into negative 20. Well, negative 18 plus negative 2 equals negative 20. Okay, J says, so far we've only considered simple regression models for this data. Here are some results for multiple regression models. So here is the full estimated model there, total SAT being the response variable, and then we've got expenditure in there and percent taking in there. It turns out that there's a pretty good case to be made that percentage of students taking the SAT is a confounding variable. It confounds the apparent relationship between total SAT score and expenditure. And so this question is just asking, in what way is percent taking behaving as a confounding variable, and use the results that we've seen here and up here to make the case. And you got to be able to, your answer has to make it clear that you understand what confounding is all about. So when a variable is a confounding variable, it's like a third variable that is related to the first two variables in such a way that it's going to change the nature of their apparent relationship relative to when you didn't have the confounding variable being taken account of. So the really, really simple example we talked about way at the beginning of class, and we've seen a couple more times, is you've got a child's height versus child's vocabulary, and you say, hey, look, taller children know more words. Well, there's a confounding variable. It's age, because taller children are older, and older children know more words. Well, there's an argument to be made here. We have an initial apparent relationship between total SAT and expenditure. So it says there is some evidence that the apparent effective expenditure on total SAT is confounded by percent taking. So let's go back and just look at expenditure and total SAT by themselves, and that's this first model, Model A. Expenditure has a negative slope. So what we're saying is, as the amount of money being spent per student goes up, average SAT scores go down. Yikes. That doesn't sound very good. That sounds like we're doing harm by spending more money on education. Ugh. Well, at least that's how it would sound if you were taking this seriously as a causal relationship. But of course, in regression, we are looking at this is observational data. We're looking at correlations and associations. We are not saying that we can discover causality. But we gotta account for this. This is a little bit weird. More money spent means lower SAT scores. Now, the proposal is that percent taking is a confounding variable. So if percent taking is a confounding variable, then percent taking needs to be related to both of these other variables. It needs to be related to expenditure. It needs to be related to total SAT. So let's go have a look. Ooh, Model B. Response variable is total SAT score. Predictor is percent taking. I have a negative slope. So as the percentage of students taking goes up, my predicted average SAT score goes down. Another way of thinking that is, in states for which a higher percentage of students are taking the SAT, the average scores are lower. This makes sense. This makes sense if it's a state with a low percentage of students taking the SAT. The students who are taking the SAT are probably the ones who are going to do the best on it. States in which there are higher percentages of students taking the SAT are going to be states where maybe more students are encouraged to take the SAT. Maybe the SAT is paid for by school districts or by the state. Something's going on that's resulting in more students taking the SAT, and those additional students taking the SAT are probably different from the initial smaller group of students who are just taking the SAT in the states with lower percentages. So more students taking the SAT means, in this case, or at least is associated with, lower scores on average. Okay, that's one half of it. Now we need to look at percent taking versus expenditure. If percent taking is going to be a confounding variable, it needs to be related to both the original response and the original predictor. So let's take a look down here. Model C. I've got expenditure as the predictor variable. Percent taking is the response variable. I've got a positive slope, which is saying that states in which there is greater expenditure per student are also states in which there is a greater percentage of students taking the SAT. Lastly, I will note that the p-values and all of these are really small, so I'm going to take these seriously as being real associations. This model down here is the one that had the really, really big p-value, but we're not talking about student-faculty ratio in this question that we're on right now. So here's the logic for how percent taking could possibly be a confounding variable. Yes, I see a negative association between expenditure and SAT score, but I see a positive association between expenditure and percent taking, and then I see a negative association between percent taking and SAT score. So states in which there is more money being spent per student are states in which there is a higher percentage of students taking the SAT in the first place, and when you have a higher percentage of students taking the SAT in the first place, that is associated with lower scores on average. So it's sort of like this percent taking variable is right there in the middle between expenditure and total SAT. This doesn't prove causality, but if there were a causal relationship, we would sort of say greater expenditure leads to greater percent taking leads to total SAT. Maybe that's valid. I'm not quite sure. I should say it leads to lower total SAT from percent taking. So maybe that's valid. I'm not quite sure. We can't assume causality here, but we do have a plausible explanation for how percent taking could be a confounding variable. Now to wrap this all up, let's take a look at this multiple regression model. Multiple regression model, I have, let's see, total SAT is the response variable, and then we've got, oh my, look at this. We've got a positive slope for expenditure. In Model A, we had a negative slope for expenditure. Now that I have percent taking in the model, I've got a positive slope for expenditure. So this is saying that if we hold percentage of students taking the SAT constant, in other words, if we were to compare two states in which similar percentages of students were taking the SAT, we see a positive association between expenditure and total SAT. So if we were to take a look at two states that had roughly the same percentage of students taking the SAT, the state that spends more money per student ends up having higher total SAT scores. And this is further evidence for the confounding because the slope for expenditure changed sign. It reversed when we took account of the proposed confounding variable, or when we controlled for the proposed confounding variable, percent taking. Okay, that was long. Obviously, if this were on your exam, I wouldn't expect you to write out all the stuff that I just said in that much detail, but a fully correct answer, a full credit answer, is going to need to, first of all, demonstrate that you understand what confounding is, and then demonstrate that you have some idea of how percent taking could be a confounding variable. Okay. This is related to the previous question. How does the proportion of variability in total SAT explained by the model in J, which is this, compare to the proportion of variability explained when percent taking is a predictor variable but expenditure is not? So this whole thing about proportion of variability in total SAT explained by the model. Total SAT is the response variable. So when you see language like this, what's the proportion of the variability in blah 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 that's explained by blah blah blah, we're talking about R squared. So proportion of variability in the response variable that is explained by or that is attributable to the model. That's what R squared is. So let's go up and take a look at the model it's asking for. When percent taking is a predictor variable but expenditure is not. Okay, that's Model B. Percent taking, total SAT score. This is the one where expenditure is not in the model. And I've got a really small p-value, and I've got, there's my r-squared, 0.78. So this is that one with a really big r-squared. So if the only variable I'm looking at is what percentage of students in this state are taking the SAT, just knowing that can explain 78% of the observed variability in total SAT scores. It sounds like this matters a lot. It sounds like this is probably the big one here. What percentage of students are taking the SAT versus total SAT score. A lot of explanatory power there for percent taking. Now when we add in expenditure, what do we get? R-squared equals 0.815 or 16 or 0.82 if you prefer. So we get a little bit of a boost from roughly 78% of variability in an SAT scores being explained to roughly 82% of variability in SAT scores being explained. So a boost of 3 to 4% in the ability of the model to explain all the differences we see in average SAT scores across the different states. So we saw in this case that yes, there is this confounding relationship where it turns out there is a positive association between expenditure and total SAT score when you control for percent taking, but it also looks like this positive relationship between expenditure and total SAT score is not accounting for a whole lot. Most of the action is in percent taking. Most of our ability to explain total SAT comes from knowing the percentage of students taking the SAT. Once you've done that, if you also know expenditure per student, that adds a little bit of predictive ability. Or ability to explain total SAT, but it's not much. It's about 4% or 3%. Okay, and then the last one for this very long question. Suppose one state in your data set had an average expenditure of $5,000 per student, 65% of students take the SAT, and the average combined SAT score in the state is 864. Calculate the residual for this observation using the model in part J. So the residual is a residual refers to a single data point, and it's the observed value of the response, the actual value of the response in the data set, minus the value of the response that we would predict using the regression equation. So what we do is we plug in the given numbers for expenditure and percent taking to make a prediction for total SAT, and then we subtract that from the actual observed value of total SAT. Be careful with these numbers. Remember before, expenditure is in thousands of dollars. So $5,000 per student in this model with these variables corresponds to expenditure equals 5. It's in thousands of dollars, so expenditure equals 5 means $5,000. So I'm going to plug a 5 in up here where expenditure goes, and then for percent taking, 65%, so I'll plug a 65 in there because my unit is percentage. And you crank that all out, you should get 870.48. The 0.48, well, oh yeah, that does make sense because it's an average. So we take that, that's our predicted value, we want to subtract that from our observed value. The observed value was given to us as 864, and so 864 minus the predicted value of 870.48 is negative 6.48. Okay, 5. Suppose you conduct a two-tailed, two-sample t-test and get a p-value of 0.023. Which of the following statements are valid conclusions to draw from this test? Select all that apply. This is a nasty one. I'm actually going to go through all of these. This was used on a previous semester's final exam, and then the next question said, pick some that are wrong and explain why they were wrong. I didn't put that on here, but in this video I'm going to explain why the wrong ones are wrong and why the right ones are right. So, p-value of 0.023. Before we even look at any of these, before you even see any of the options, let's just say what a p-value is in our head. A p-value is the probability of obtaining results at least as extreme as the results we obtained, assuming the null hypothesis is true. There are slight variations on how to say that, but that's the general idea. Here it is right there. There is a 0.023 probability of getting results at least as extreme, assuming the null hypothesis is true. That is the straight up definition of a p-value right there. Here are two things that are not the definition of a p-value. there is a 0.023 probability that the null hypothesis is true. No, 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 no. This is the mistake that so many people make. I think the reason so many people make it is because this one is easier to understand. It turns out that the wrong interpretations for the p-value make more intuitive sense than the correct interpretation of the p-value. That's unfortunate, but we're using p-values, and so we better know what they are. The p-value is not the probability the null is true. The p-value is the probability of getting data at least as extreme as yours, assuming the null is true. And then A is just the converse statement of B. These two statements are equivalent. They're both wrong. Okay, D. There is a 0.977 probability of getting results at least as extreme, assuming the alternative hypothesis is true. This sounds like the converse of C. It almost sounds like this should be right because, hey, I just took 1 minus 0.023 and got 0.977, and so if I'm going to do the converse there, or the complement as we call it, then I should also switch between null and alternative. Doesn't work that way. The problem here is that it's easy to assume the null is true because the null is just one value. It's usually 0. If it's in fact it is. If it's a two sample t-test, then the null is difference in population means equals 0. What value do I pick if I'm going to assume the alternative hypothesis is true? There are an infinite number of values that are not 0. It's not quite clear how this is supposed to work. There are some methods that try to do this, but we haven't talked about them at all in this class. We are not computing, when we compute a p-value, we are not assuming the alternative is true, we're assuming the null is true. So D is wrong. E, there is a 0.023 probability that these results occur due to chance. Oh, it sounds so close to what's correct, but it's wrong as well. E is just a casual restatement of A and B. E is basically equivalent to A and B. When people say the results occur due to chance, that sort of implies the null is true. When we say the null is true, we're saying the variability we observed, it's not due to the proposed phenomena in our scientific hypothesis, it's just due to quote-unquote chance, which usually just means due to stuff that we don't understand or can't explain or haven't accounted for. So this is just a different casual way of saying there is a 0.023 probability that the null hypothesis is true, and that's not what a p-value is. F, the sample means would be considered significantly different at the alpha equals 0.05 level. Yes, indeed, that is true. I got a p-value less than 0.05. That means I'm going to say these means are significantly different from each other. G, the sample means are more than one standard error apart. This is a tough one. It's correct. There's actually two ways of thinking about this. Means are more than one standard error apart. Think back to how we make that t-test statistic. It's the difference in sample means divided by their standard error. So if the means were one standard error apart, we would get t equals 1. If you think back to the t-statistics we've looked at in the past, t equals 1 produces a large p-value. You could think of, if you don't remember the values of the t-statistics themselves, think about the distribution. Maybe I'll draw it on here. I should have drawn it on these solutions, but think about, this is t, and there's 0 in the middle. One standard error is just one standard deviation of the sampling distribution. So one standard deviation. Remember that I probably didn't draw that quite far enough out, but we have 68% of values in a normal distribution, which a t-distribution is just about a normal distribution, being within one standard deviation of the mean. So if I had t equals 1, my p-value would be whatever is left over in these tails, which is 1 minus 0.68, which is 0.32. So if I have if my sample means were one standard error apart, my p-value would be about 0.32. It would be really big. The other way to think about this, another way to think about it is we have about 95% of the data within 2 standard deviations of the mean, so 95% in the middle means 5% on the outside, and so roughly t equals 2 is what gets you a p-value of around 0.05. The other way to think about it is in terms of confidence intervals. So one standard error. Well, the way I make a confidence interval, I get a margin of error, and a margin of error is 2 standard errors. I double the standard error, I add and subtract that 2 and from my my point estimate, which is in this case a difference in sample means, and I got a p-value that's small, which means 0 is outside the confidence interval. If the width of my confidence interval is 2 standard errors and 0 is outside of it, and I built the confidence interval, actually, sorry, the margin of error is 2 standard errors. The width of the confidence interval is actually 4 standard errors, but let's just look at one side of it. The margin of error is 1 standard error. That's from the center of the confidence interval to one endpoint, and 0 is outside of it, and the center of the confidence interval is the difference in sample means. That means that if I have a p-value of less than 0.05, then my difference in sample means has to be actually more than 2 standard errors apart, because when I took that difference and I put a margin of error around it, that is 2 standard errors, I still didn't contain 0. If that was weird, the picture of it is down here. This explanation actually works for J as well. Okay, H. If we repeatedly take new random samples from the same population, we expect to reject the null hypothesis 97.7% of the time? No. This repeatedly taking new random samples from the same population, that's part of something that is correct for some of the stuff we've talked about. This is repeated sampling. This is how you get sampling distributions. But the p-value for one sample doesn't tell us what the success rate is going to be for future samples in terms of reject or fail to reject the null. The closest thing this is kind of like is if we were interpreting a 95% confidence interval, we could say if we repeatedly take new random samples from the same population, we expect that whatever the true population difference is will be captured within 95% of all confidence intervals. If we were talking about p-values, we could say if we assume the null hypothesis is true and then take new random samples from the same population, we should only get p less than 0.05 5% of the time, but that is not what it says in H. Okay, I and J are very similar. So I says if we use the same data to construct a 95% confidence interval for the difference in means, it will not contain 0. Yes, the p-value is less than 0.05. If the p-value is less than 0.05, the corresponding 95% confidence interval is not going to contain the null hypothesized value, which in this case, because it's a 2-sample t-test, is 0. And then J is just kind of a more complicated way of saying I, which is very similar to what we said in G, which is if we use the same data to construct a 95% margin of error for the difference in means, it will be smaller than the point estimate for the difference in means. This is kind of what I was trying to explain with J. So here is a line. And we know the confidence interval doesn't contain 0. We've already established that, and so our point estimate is somewhere. X bar 1 minus X bar 2 is somewhere. We have some interval we've put around it, and we know that after we put that interval around it, 0 is not inside the interval. So it's got to look something like this. We're going to have a confidence interval, the center of which is X bar 1 minus X bar 2, and then 0 is not inside that confidence interval. Well, this difference right here, that is a margin of error. That's one margin of error. That's how we get to one of the endpoints of the confidence interval. So if that is a margin of error, this, whatever this value is, that is the size of the difference in means. Here's 0, here's the difference in means. So that number, whatever it is further away from 0 than this thing. So whatever this number is, it's got to be bigger than that margin of error. Otherwise, 0 would be inside the confidence interval as opposed to outside. Okay. 6. Suppose we have a data set with the variables wealth, age, school, and hours. I've not defined these, but you can sort of take a guess. In each, you know what? Let me delete all the scribbling from up there. Okay. Okay. In each scatter plot below, the x or horizontal axis variable is given, but the y or vertical axis variable is not given. Use the provided correlation matrix to identify which variable is represented on each y-axis. And it says you don't have to write down the correlation coefficients, just fill in the name for each y-axis. So the x-axes are given here, age and age, hours and hours. I've got this table down here full of correlations, and I want to figure out what are the y-axes on 1, 2, 3, and 4. And you know what? I just realized, oh wow, how about that? I just realized I made a mistake in my solutions. It says you don't have to write down the correlation coefficients, just fill in the variable name, and I went and did the opposite on my solutions. Well, it says you don't have to, and I did. So when students did this, I did count it as correct, but really I should be putting in the variable name. So I'll do that here in this video. Okay, let's see. I've got 2 negative correlations and 2 positive correlations. I can note that right off the bat. So let's see. Age and age. And then negative correlation. So age, this is kind of tough actually. For age, if I go down here, I've got 3 negative correlations. Age is negatively correlated with all of my other variables. And it's the same, you could go across here. If I read it down the column, down the row, I get the same numbers. So I've got 2 plots with age on them. I've got 3 negative correlations. And they're not that far apart from each other. Negative 0.52, negative 0.72, negative 0.85. This is actually kind of tough. Let's take a look at these two. Hours. And I've got 2 positive correlations. Let's see. Hours. Oh boy. There we go. Hours. And you can look at hours over here as well. I've got 2 positive correlations for hours and 1 negative correlation. All right, well, the negative correlation isn't one of these because I see when I have x-axis equals hours, I've got some positive correlation. Just as a really quick aside, I forgot to mention this. These ones are just nonsense. This is the correlation of wealth with wealth, age with age, school with school, hours with hours. Any variable is going to be perfectly positively correlated with itself. So these don't mean anything. Okay. So I've got my 2 positive correlations with hours, 0.82 and 0.53, and so the one that looks like a stronger correlation, the one that seems to suggest more of a line, or the one for which the data would be less spread out around the line, if I were to draw the line through it, is going to be the one with the larger correlation. And so I think it's pretty clear when you look at these two right here that 4 has the stronger correlation and 3 has the weaker correlation, so 4 has got to be the 0.82. 3 has got to be the 0.53, and I should follow my own instructions here and write down what these are. So this is y-axis is wealth, and then for 3, y-axis is school. Okay. I told you 1 and 2 were looking like they were a little bit too hard before, but they are actually going to be solvable now that I have some basis for comparison. Check out what we got, 0.53 and 0.82, and before when we were looking at age, we were trying to choose between negative 0.72, negative 0.52, negative 0.85. Oh, well, hey, these 2 negative correlations are about the same value as those 2 positive correlations. This looks awful similar to this as far as strength of correlation. If this is positive 0.53, this isn't going to be, it's going to be a negative number. It's not going to be a whole lot more than 0.53. My options are 0.52, 0.72, and 0.85. There's no way this is 0.72. If this is 0.53, and this looks like it's about the same amount of correlation, this has got to be negative 0.52. And then finally, this one right here, check out that versus that. This correlation looks like it's about the same strength as this correlation. If this one's positive 0.82, that one's got to be negative 0.85. And so negative 0.72 is actually the odd one out here. So I'll go back in and say the names of these things. So we have age versus school, And then over here I've got age versus hours. The other way you could have done it, and this is a little bit tricky, if school is the y variable in both of these cases, then the data in terms of the y dimension are going to be distributed exactly the same way. It's the same data on both of these y-axes. Check it out. That point right there, that point right there, that point right there, that point right there. I got 1, 2, 3, 4, 5 hanging out here. I got 1, 2, 3, 4, 5 hanging out here. Check out that point and that point. Oh, up top I got that, and that, and I got that, and that. If you were only looking in the vertical dimension, you would notice that the axes for this plot, the y-axis for this plot and the y-axis for this plot, have to be the same variable. I don't expect people to solve it that way. I think the way I just went through it is the easier way to do it, but that's another way of doing it. Okay, 7. Explain the difference between what standard deviation quantifies and what standard error quantifies. Well, we're going back with this one. So we first saw standard error in Module 4 on sampling distributions. And we first saw standard deviation before that. So let's go back to standard deviation. Standard deviation is how much variability is there in the data, or how much variability is there in the values that this variable takes on. If we want to use the word standard deviation itself, this is one of those lovely statistics that actually means like what it sounds, which is means like what it sounds, means what it sounds like, which is the standard amount of deviation. And the word deviation refers to deviation from the mean. So the standard amount by which the data tend to deviate from the mean. That's standard deviation. So if standard deviation is bigger, the data are more spread out around the mean. Okay, standard error. Let's apply that same method. The standard amount by which there is error. The standard amount, well, error. Error in this case refers to using a statistic to try to estimate an unknown population parameter. We saw this when we were talking about using x bar, the sample mean, to estimate mu, the population mean. If I pull a sample and I take the average of that sample, the average of that sample is not going to be the same as the population average. Probably. I'd have to be extraordinarily lucky to get a sample mean that is exactly the same value as the population mean. So there's error in my use of... There's error when I use the statistic as an estimate of the population value. How much error is there? Well, I don't know, but I know what the standard amount of error is. So the standard error is the standard amount, not by which data tend to deviate from the mean, but the standard amount by which statistics tend to deviate from the population values that they're being used to estimate. And that's a good enough answer for this question. The other way you can think about standard error is data has a distribution. So like the normal distribution. My height is normally distributed, so then the distribution of height looks like that. Statistics have distributions too. We call them sampling distributions. A sampling distribution is the distribution of values a statistic takes on under repeated sampling. If you were to keep taking new random samples from the same population over and over and over again, you compute the same statistic for every sample. The sampling distribution is the distribution of values that that statistic takes on, and so the standard error is just the standard deviation of the sampling distribution. So standard deviation is for the distribution of a variable. Standard error is the standard deviation of the distribution of a statistic, which we call a sampling distribution. Last page. Number 8. Suppose 4 different one-sample t-tests are conducted. Tests, we're going to call them A, B, C, and D. Each test is from a different sample. The sample size for each test is the same, and each test is done using alpha of 0.05. The diagrams below, by the way, the only reason I mentioned the sample size being the same is because these are t-tests, and degrees of freedom depends on sample size. So this is just saying the degrees of freedom would be the same for all of these. The diagrams below show the sampling distribution of each test statistic under the null hypothesis. For each diagram, the shaded area is the p-value. Ooh, okay, so I got shaded areas, shaded areas, shaded areas, shaded areas. I didn't realize my pen was on. Let me erase that. I got some shaded areas, and those are all p-values. And then the value of the test statistic is given. Well, the p-value is the area in the tail of the curve next to the test statistic. And then we've also given the values of these shaded areas. So shaded area equals, you can read that as p-value equals. Okay, so let's answer these questions. A, which of the following are plausible values for the p-value for test D? Circle all that apply, and I've got -1, well, okay. P-value, it's not going to be negative. So this one's straight out, this one's out. P-value is only 0 if I shade 0 of the curve. The p-value is never exactly 0. Sometimes it's extraordinarily small because my test statistic is like way out here. P-value is never exactly 0 unless you have some, well, you can come up with some ridiculous case in which it is, but we've never seen that. Okay, and then I've got actual realistic looking values for p-values such as 0.01, 0.02, 0.04, 0.06, and 0.1. And I want to know which are plausible for the p-value for test D. So that's D. So this little area under there next to -2.6, what could that area be? Well, let's see what information we have. I know that the area next to 1.9 is 0.034. Now this is on the right side of the curve, and this is on the left side of the curve. It doesn't matter. This curve is symmetrical. So if the area next to 1.9 is 0.034, then the area next to -2.6 is less than 0.034, and you can see it just by looking too. So I need to pick the values that are less than 0.034. Those are 0.02 and 0.01. Okay, B, for a right-sided test using whatever sample size was used in these tests, what value or values for a test statistic could plausibly result in the decision fail to reject the null? Okay. Well, I know that this one results in the decision reject the null because my p-value is 0.034. Let's note that it's talking about a right-sided test. So we're not doubling the p-value. That's actually the next question, but if we were doing a two-sided test, I'd be doubling this, but it's a right-sided test. So I know that this results in reject the null because my p-value is less than 0.05. So if I get a test statistic of 1.9, I'm rejecting the null. Here we go. Test statistic of 1.5. P-value is, ooh, it's bigger than 0.05. This one has failed to reject the null. So somewhere between 1.9 and 1.5 lies the cutoff for my test statistic, on which one side of the cutoff is reject the null and the other is fail to reject the null. Which is it closer to? It's probably somewhere in between the two. Maybe it's roughly in the middle. This isn't, the relationship between different test statistics and p-values isn't linear, but this one is a little bit below 0.05. This one is a little bit above 0.05. So somewhere between there. And if I'm looking for test statistics that are going to result in fail to reject the null, I'm looking for ones that are smaller. So I know definitely test statistics smaller than 1.5 are going to result in fail to reject the null, because if my test statistic is smaller than 1.5, this cutoff is further towards the center of this distribution. My p-value is bigger. So let's see what we got going on right here. 2.2, 2.0, 1.9. It can't be any of those. 1.9 results in reject the null. 2.2 and 2.0 are bigger than 1.9. 1.6. Well, I don't know for sure, but 1.6 is closer to 1.5 than it is to 1.9. It's looking like 1.6 is probably going to result in fail to reject the null, but at least it's plausible that it does. I don't want absolutely definitely, but plausibly, yeah, 1.6 could do it. And then all the ones that are smaller, 1.4, 1.2, 1.0, 0.8, these are all test statistics that are smaller than this one, which we know results in fail to reject the null, and so these statistics must also result in fail to reject the null. Okay, is the sample mean significantly different than the hypothesized mean in test B? Briefly justify your answer. Test B, okay, let's see. how am I going to decide if the sample mean is significantly... Ooh! If the difference is significant, the p-value is less than 0.05. Well, what's the p-value here? This area right there, to the right of 1.9, or you know what that is, that's 0.034. All this is the difference between a two-tailed test and a one-tailed test. When I go from 1 to 2 sideds for the test, I just double the p-value. If that area there is 0.034, so is that value. So 0.034 times 2 is 0.068. That's bigger than 0.05, so fail to reject the null for B. D, if you were to make a 95% confidence interval for the mean in test A, would it contain the hypothesized mean? Briefly justify your answer. So, test A. Okay, if I'm going to make a confidence interval, this question's kind of tricky. I actually feel sort of bad about asking this question, but hey, it's the practice exam, so this is the closest thing to a trick question on this entire exam. We are so used to saying, if the p-value is less than 0.05, that means reject the null. If I reject the null, then the hypothesized value is outside of the confidence interval. And so it says, would the confidence interval contain the hypothesized mean? Oh, well, I rejected the null, so no. Well, here's where the trick comes in. When we relate confidence intervals to p-values, a 95% confidence interval corresponds to a two-sided hypothesis test. So if I get a p-value less than 0.05 from a two-sided hypothesis test, then the hypothesized value is not going to be in the confidence interval. It's not necessarily the case for a one-sided test. And I actually already know from the previous question that if I took this and I turned it into a two-sided test, my p-value would be bigger than 0.05, which means if these were my results and I made a 95% confidence interval, the 95% confidence interval would be agreeing with not the right-sided test, it would be agreeing with the two-sided test. And the two-sided test results in fail to reject the null, which means the hypothesized value would be inside the confidence interval, not outside of it. And again, I'll concede that is a tricky question. Okay, and then the last one says, oh, you can't read this because of how my screen's set up and I can't scroll down anymore, so let me see if I can move this up. Almost. There we go. Which test resulted in a statistic that would be most unlikely to occur by chance if the null hypothesis were true? Oh, this isn't too bad. After all these weirdo tricky questions, this one seems relatively easy. What is this talking about? A statistic that would be most unlikely to occur by chance if the null were true. The p-value is the probability you would get a test statistic at least as big as the one you got just by chance if the null were true. This is referring to a p-value. It's a little bit, this language is a little bit casual the way it's been worded here, but this is referring to a p-value. So we want the one that's most unlikely to occur by chance, which means we want the one with the smallest p-value. D has the smallest p-value. We already said that on a previous one. Okay. I hope this has been helpful for you. I hope as you go through this video, I realize I just made a really long video, so hopefully you can scroll around on the YouTube channel and see which question I'm on for these explanations. When it comes to practicing for the final exam, I always recommend doing this without seeing the answers first, so I hope before you watched this video you actually attempted this stuff. But if you didn't, pull out a blank version of the exam and try it now. Don't work on the exam with my solutions right next to you. And again, I hope this helped. Best of luck on the final exam, and that'll be the last video for the semester, so see ya.